All right, so hello everyone. Can you all hear me okay? All right, cool. So as Andrew said, my name is Paul Jeffries. I work at Ramble, where I am computational design lead and chief digital zoologist is my official job title. So I basically look after Grasshopper and all the other animals. So I'm ably assisted today by Emily, who's somewhere behind the column, and these guys as well. So if you have any questions, stick your hand up and they will help you out. So what we're going to cover today, we're going to go on to Grasshopper, but before we get on to actually talking about Grasshopper itself, I thought I'd give you a little bit of an introduction and a little bit of theory behind computational design, parametric design, whatever you want to call it, and really kind of what it is that we mean when we talk about these things, and why we think that they're valuable for you to try and learn it. And then we'll also do a little bit more just looking at Rhino geometry in general and just talking a little bit about the sort of theory behind that and how it works. And then we'll actually get on to Grasshopper, so we'll get on to the good bit as well today. So I thought I would just start by talking a little bit about the terminology, because there are lots of different sort of phrases that get brought up when we're talking about parametric design and computational design. And it's a little bit difficult to define most of these because it's such a kind of new and emerging field that lots of different people use these different terms in different ways. So there's all sorts of terminology around, like digital design is usually used as sort of a catch-all for it. And then computational and algorithmic design kind of is a subset within that. And then there's parametric design, which deals with modeling stuff via parameters. And then there's all sorts of other things like computational optimization and generative design, which falls into that category. There's also BIM, which some people either see as an overarching kind of all-consuming thing or a subset of this. And well, my view on it is that it's sort of a slightly separate thing that has some overlap. So we're not really going to be talking about BIM at all. You might be glad to know. And then there's also certain other things like parametricism, which are slightly more sort of architectural takes on this technology. And we're not going to talk too much about that either, because that's sort of an architectural style and an architectural philosophy, which doesn't necessarily relate too much to what we do as engineers. So what we will do is we'll talk about parametric design, computational design, and what I wanted to do first of all is just give you kind of my interpretation of what computational design is all about, what it is that we're really talking about here. And in order to do that, we need to first of all talk about design in general and the design process. So in this diagram here, running across the middle of the screen, in those little blue arrows, those are the REBA stages of work. So you may not have come across those already, but you probably will do when you enter practice. Those are kind of the official stages that a project goes through in the UK and in a lot of other places, which starts off with kind of different phases where you start off defining your strategy and then you go into concept design and then develop design and so on and so forth as you get closer towards developing stuff. So that's the kind of the framework that a lot of us operate to. But then over the top of that, in a much more messy diagram, because it's a much more messy process, I've drawn essentially what the design process actually looks like from the point of view of someone involved in it, which is a lot more networky, a lot more backwards and forwardsy. So you might start off at the beginning with some sort of brief that your client is giving you. You then have to go away and understand that brief and talk to the client and develop some feel for what it is they actually want. That might lead to you generating some ideas, some initial concepts. You might try and communicate those back to the client so you get some more feedback on that and you kind of enhance your understanding of what it is they're asking for. And then from that you go on to develop that design further. You decide on some core principles which are going to define how your whole design is going to work. You perform some calculation and analysis and testing of that design, and then all that has to be communicated back to the client, so there's another kind of loop there. That might then result in the brief changing or being refined, and so on and so forth. So you go through all these different stages, often very cyclically, until you get to the end where you actually, hopefully, build the thing and everyone gets paid. So that is how the process actually works. It's a little bit more messy than a set of neatly ordered stages. But what I have done when drawing this out is I have categorized these activities into the mental activities above the line and the physical activities below the line. So when you're designing something, part of that goes on in your head, part of that goes on out in the real world. You have to kind of use your imagination and your brain power to work out how you're going to solve the design, but you also need to do a lot of physical stuff, a lot of kind of calculation and drawing and developing models. So you have these two different parts of the design process. And you might think of this as creating a mental representation of the design, which is you kind of understanding and thinking about what you're doing, and then a physical side to it, which is usually testing out those ideas, creating physical models, and then communicating that to people. The physical side of things these days might very well often actually not be physical in the literal sense. It might well be virtual. And as time has gone on, the way that we've used computers in engineering has kind of accelerated more and more. So whereas previously we would have had draftspeople in the office, drawing diagrams and drawings and details all by hand, we now have CAD technicians and engineers themselves, of course, using CAD software in order to draw those things in the computer instead. Previously, back in the good old days, if we wanted to look at what a building might look like in 3D before we built it, then we would have to construct a physical model and actually stand around it and look around and see what it looked like from different angles. Whereas now we can build a 3D model inside the computer. We can visualize that in various ways. We can look at it, we can interrogate it in slightly more detail than we can a physical model. And of course, previously, you'd have to do a lot of hand calculation, you'd have to look up stuff on tables and do all that sort of thing. And that process itself has also been largely put into the computer. So we have a lot of different analysis packages now that can help us to do those calculations. We don't have to do them all by hand anymore. So these are all ways that computers are being used in design, but these are not necessarily what I would call computational design. So I'm a bit of a computational design snob, and my view is that it's not just using computers in design. And the reason that I say that is because all of these different ways of using computers were essentially taking the original physical process and then trying to replicate that as closely as possible inside the computer. And that was a very sensible thing for them to do at first, to help people adjust to that paradigm shift, but it did miss out on a lot of opportunities. So instead of just drawing stuff with a pencil or on a sketching pad, they made it so you instead draw with a mouse on a screen. But the basic kind of processes that you go through both physically and mentally are not too dissimilar there. Whereas what I think is that the ability that computers have and the potential that computers have is actually a lot more than that. If you're treating a computer as just a simple static, change it once and never modify it again kind of thing, then you're missing out on a lot of the powers of computers, because computers are inherently dynamic, they're inherently logic-based, they're inherently process-driven. So, because computers are process-driven, and because they can deal with logic, it's actually possible to use them not just to mimic the physical side of the design process, but also to have an influence and to have applicability to the mental side of things as well. So we can take the logical model that we have to build up in our own heads, and we can now express that far more closely than we could before inside the computer. Because we can take the logical processes that we use and the logical processes that a computer uses, and they are to a certain extent compatible and kind of equivalent. So to give you an example of how that's useful, if you're going to set out a column grid, so as you probably have seen, when you're arranging columns in a building, it's very common to use some kind of regular grid arrangement to do that, so that you end up with equal spans and so on. And if you are going to describe that column grid to somebody or to a computer, then you could do it by saying, okay, this column here, this first column, that's at these coordinates here. So x equals 10, y equals 500 million, and so on and so forth. And then you can say, this next column here, this is at these coordinates, and this next column is at these coordinates, and so on and so forth. So that is one way that you can describe stuff. And when you're drawing something by hand, or when you are manually drawing these things inside a computer, that is essentially what you're doing. However, that is quite time-consuming to kind of describe that to someone. It's not a very natural way to talk about this thing. What's a more natural way of talking about this is to say, you've got 6 columns spaced 8 meters apart. And by saying that, you can define that whole column grid in a much simpler and more parametric way. And through using parametric tools, using computational design tools, that's the kind of thing that we can start expressing in the computer. So we don't have to anymore tell the computer these columns are at these positions. We can tell the computer the logical rules that set out those columns and then have it interpret the results for us. So we can, for example, then build up 3D models like this, where that logic is embedded, and where we can simply, by adjusting the column spacing or the overall width of the building or various other parameters like that, we can then instantly see the effects on that geometry and regenerate it without having to do the mental work ourselves of actually, going through and working out what the implications for that are on every single possible member and nut and bolt in the building. Because we can tell the computer how to work that out for us. So this is my personal kind of one-liner definition. If someone asks me what's the difference between computational design and regular design, I say it's a change in the medium of design expression from geometry to logic. You're no longer working purely with geometry, you're working with the logical processes that define that geometry. And that may seem like it's sort of a step away from the final design. It's more of an abstraction. I would say it's actually less of an abstraction because it's actually more closely modeling the process that you have in your head. You're having to make less compromises to deal with the medium that you're representing your design in. And there are a number of advantages to taking this approach. So one is automation. You can take away a lot of the busy work, a lot of the boring stuff, a lot of the kind of day-to-day stuff that you have to do. You can take processes to sort of convert geometry and data between different formats so that you don't have to completely remodel everything between different packages of software and things like that. So that's one advantage. Another advantage is being able to handle large quantities of data. So this example on the screen here is something that I worked on last year. What this is doing is it's checking to see whether there are going to be any problems on a building facade from solar glare. So in other words, as a train drives past this building, is the sunlight going to reflect off the windows into the driver's eyes, mean that he can't see the stop signal or whatever, and potentially cause problems? That's what this is checking. And the analysis behind that isn't super complicated. It's sort of GCSE physics. It's just about reflection angles and stuff like that. But by building this into a parametric tool, we could check hundreds of possible train positions and against I think about 500 windows this building had. We can check each one of those windows individually, check the reflections from them, and see how likely they are in order to dazzle the driver. And it's not a complicated process, but it is a lot of data to have to do by hand. And by automating that, we can actually do this kind of analysis much more easily than we did before. We can also look at more complex types of building forms because the computer can do a lot of heavy lifting for us. And in fact, a lot of kind of complex geometry isn't actually that complex when you get down to it in computational terms. It's a lot easier to express some types of geometry kind of mathematically than it is just to kind of describe it to another human. And computers are very good at dealing with those kinds of geometries. What you can also do with those more complex geometries is take them and rationalize them. You can sort of essentially take a freeform shape and then you can apply a set of rules to that which are going to essentially render that freeform shape into much more buildable, repeatable modules. So in this example here, I was looking at a sports stadium roof which had a freeform geometry, and initially every single panel on top of that building was going to be a different shape slightly. But by applying some computational logic to this and by optimizing it, we took that huge mass of different shapes and we rationalized it down so that it was made up of only 14, in this case, different types which could be repeated in different combinations in order to still keep that same shape within an acceptable tolerance. And that, again, is something that it would be very difficult to have to do by hand, because you might choose a bit of a set of panel sizes to begin with and then find that they don't fit. But in this, we could do it in an iterative way that would help out and let us actually resolve that problem. Finally, it helps to communicate and collaborate, and actually helps you to enhance the overall design. So this is something that Emily and I hacked together a couple of weeks ago. It's a parametric tool building analysis tool, essentially. So what this lets you do is to play around with various parameters of the building, and what it is then showing on that spider diagram there are several KPIs, key performance indicators of that building. Stuff like how much floor area you've got, stuff like what is the deflection of the core, how much concrete do you need to actually build this, stuff like that. And the way that this would traditionally be done is that when you're designing a tall building, the architect might come to a meeting and they'd say, okay, in order to meet my lettable floor area targets, I'm going to have to increase this depth by this much and put an extra floor on top maybe. And then the vertical transportation guy, the guy that's looking at the lifts, will say, okay, I'll go away and I'll look at that. And then the meeting next week, he'd come back and say, okay, that means we need another lift. So then the structural guy would go away and they'll say, okay, that means our core's going to get bigger, we'll have to rearrange that makes it a lot stiffer. And then they'll come back to the meeting the next week, and then you finally might have an idea, except then that core has got bigger, so it's reduced your lettable area, so now the architect is going to have to say, oh, actually, I'm going to have to now do this over here as well, and so on and so forth. So by doing that parametrically, we can reduce that whole process, which involves multiple people and often a long period of time, down into something which is done instantaneously and that you can just see. So you can sit there in a meeting with all these people, you can play around with the sliders, you can say, okay, these are the trade-offs, this is how we can balance those. Or if we can't balance those, here's how we have to move that on first. So your iteration speed is greatly increased, and the more you can iterate a design, the better you're able to improve it, the better you're able to make those trade-offs, and ultimately the better your design will be. So that is kind of my pitch to you as to why you should care about this stuff, because they're not going to examine you on this, so you might think, well, who cares? I mean, you're here, so probably some of that work has been done, but this is why I think this stuff's important, this is why I try and push this stuff. Ultimately, my belief is that it leads to better designs. Okay, so that's enough about that. What we'll move on to now is a little bit more mathematical, and that is actually looking at NURBS themselves. So I think Laura talked to you a little bit last week. Actually, let me just pull up a file. So in Rhino, actually I won't do that. Let's do it on the slides instead. So as Laura showed you last week, different curves in Rhino. Different curves look different, but they are all essentially defined in the same way. Let me pull that out. So curves in Rhino have two important qualities. There's technically a third one, but we won't talk about that because it doesn't really come up very much. They have control points, and they have a value which is called their degree. So the control points are used in order to determine the geometry. So in this table here, we have got 3 different curves. Each one of those has exactly the same control points, but they've got a different degree number. And what that degree represents, and what that degree controls, is, first of all, it's the degree of the polynomial equation, which is describing that curve. So some examples of polynomial equations over here, if you didn't know what those are. The degree of those polynomials is the highest power in that equation, so the highest power of whatever your parameter is. So in this case, here I've got y equals ax plus z. The highest power of x there is 1, so that's degree 1. Y equals ax plus bx squared plus cx to the power of 3 plus z or whatever, that's degree 3 because the highest power of x is 3, and so on and so forth. So that's mathematically what that means, but in terms of the actual geometry, what that means is, what that is controlling is the number of control points that each point of these curves is being influenced by. So you take that degree number, you add 1 to it, those are the number of control points that each point along here is caring about. So in a degree 1 curve, we start at that point there. This curve is being influenced by that control point there and that control point there, and it's just smoothly linearly interpolating between those. It then gets to that point, and now the 2 points that it cares about are that one, and it just linearly interpolates between the two. If we had a degree 2 curve here, then it would start off similarly, but it would be looking at the 3 different control points at the start of this curve. So it would sort of start off there, but then it would gradually be pulled towards this point over here. And we can see that in the degree 3 and the degree 5 curves. In the degree 3 curve, each point along here is being influenced by 4 different points. So each point is having a pull on it, but as you can see, it's only ever actually touching that first point and that last point. These other points, it's kind of being pulled towards, but it's never actually quite reaching them. In the degree 5 curve, same effect, but even more pronounced. So the higher the degree, the more control points the line is essentially being smoothed between. So the higher the degree, the smoother the curve. And that works for surfaces as well. So with surfaces, you can have control points and you can have degree values, but whereas curves only have one sort of string of control points, which controls their geometry all the way along, surfaces, as I think Laura showed you last week, they have this grillage of control points. So they have control points in 2 directions, and they also have a degree in 2 directions. And one thing that's important to know about surfaces when you trim them, such as this last shape here, that curve there has exactly the same set of control points as these two as these 2 surfaces here. So when you trim off parts of a curve, parts of a surface, or parts of a curve, you're not actually getting rid of any control points there. That grillage still exists behind the scenes. What you're doing is you're adding in an extra layer of information which just tells Rhino this part of the curve exists, this part doesn't. And the reason that I mention that is because you may find sometimes in Grasshopper some components will take in a trimmed curve, but they will still treat it as if it's the full untrimmed curve, full untrimmed surface even, that you started from. So the next thing I want to talk about is curve parameterization. So I showed some equations on one of the earlier slides in the form y equals something x, but you can't actually express curves in 3D space in that way without limiting yourself to only having one x value per value of y and vice versa. So if you have a curve which is going to kind of curl back on itself and cross over the axis and tie itself in knots and stuff like that, then it's difficult to express that in that way mathematically. So what you do instead is you define a curve in terms of another parameter, which is often called t in Rhino. So rather than just having one equation, which is y equals something x, what you have instead is one equation, which is x equals something t, y equals something t, z equals something t, and then you can find any point along that curve with reference to that extra parameter t. And you will have a value of t at the start of your curve and a value of t at the end of your curve, and that is known as your curve domain. So in this case here, we have a line between that point there and that point there. So if we express that parameter t from 0 at the start of the curve to 1 at the end of the curve, then you can find any point along that curve just by plugging that parameter t into these equations. So if you want to find the position at the start of the line, then you plug 0 into that and you'll get 1, 1. Or if you want to find the end of the line, you can plug in 1 into that and you'll get 3, 4. So this is a way of representing curves mathematically, and the reason I bring this up is because very often in Grasshopper you will start to see these t values appearing, and you will need to define positions along curves by this t value. And there are a couple of pitfalls that you can kind of fall into that if you don't know what that actually represents. So one thing is that you don't necessarily know what the domain of any curve is going to be. It could be something fairly random. So for example, in the case of this curve, we've got a domain that goes from 0 at the start to 138.14 at the end. The other thing to be aware of here is that your parameter space along a curve is not going to be uniform. So what I mean by that is that this point here has a parameter t of 33, and that point there, which is sort of 2/3 along the curve, has a parameter of 120. But hopefully you can see just from looking at this that that distance there is not proportional to that distance there in the domain space. So you can think of these curves as kind of like elastic bands where you're pinning parts of them down and stretching parts of them out and things like that. If you had your elastic band when you started with it and you just neatly marked off centimeters along it, after you'd stretched it out and moved it around and pushed and pulled it and done whatever with it, you might expect to see some deformation in that, and those markers would no longer be 1 centimeter apart. They, could be, because different parts of that might be stretched in different ways. And it's the same with curves in Rhino. So if you are defining positions along a curve with relation to parameters, just be aware that you can't necessarily map length to that. There are other ways of pointing out points at a particular length along a curve, and it's not the same as defining the parameter. And the same thing applies to surfaces, except again it's in 2D. So rather than having one single parameter value which you can use to select any particular point on a surface, you instead have two, which are typically called U and V, and they essentially work. You can think of these surfaces as being a bit of graph paper with their own local axis system drawn on it. If those two axes on the graph paper are marked U and Y instead of X and Y, then you get an idea of how that works. You can draw a point on that graph paper. That will be defined relative to that surface. If you move that surface around in 3D space, then that point's position in 3D space would move, but the parameter position of that on that surface would not. So these are just ways of defining particular positions on curves and surfaces. And after that's all over, we can now actually get on to the fun bit and start looking at Grasshopper itself. So if you open up Rhino and you type in Grasshopper if you haven't already, so I'll just close that and then type in Grasshopper. So hopefully you're all fairly familiar with Rhino and the Rhino interface from last week. I know Laura also touched briefly on Grasshopper last week as well, but what we'll do in this session, first of all, is just kind of go through very kind of, slowly and methodically, and just kind of cover the different parts of this interface and what they do, and actually then kind of talk about how you use Grasshopper in a fairly kind of slow and steady way in this first session. So the pace will pick up in later sessions, but for this one, I really just want to make sure that you all understand the basics so that we have a solid foundation to build on, basically. So this window here is Grasshopper. So Grasshopper has its own little sub-window that sits inside Rhino. And let's just run through this interface quickly. So up the top here, you've got a title bar, like many Windows programs. One nice thing about this in Grasshopper is if you double click on that top title bar, you can cause that window to just roll up to that top title bar. So if you are doing some work in Rhino and Grasshopper simultaneously, and you've only got one screen, and you want to see what's going on behind Grasshopper, then you can just use this little trick to kind of get the Grasshopper window out of the way very, very quickly and easily. Just below that, we have got a fairly standard, Windows menu bar. So the file menu lets you create new documents, open documents, save documents, so on and so forth, all very standard. The main thing I want to point out here is that the documents that Grasshopper uses are separate to the documents that Rhino uses. So they are to an extent independent of one another. So if you save your Rhino model but don't save your Grasshopper definition, then the next time you open it up, you'll have lost the Grasshopper definition and vice versa. So just make sure that you are saving your Rhino file and your Grasshopper file both. It's pretty good about reminding you these days, so it's not a huge problem usually. Just be aware of that. And also, it is possible to use Grasshopper definitions with multiple different Rhino files, but very often you'll want to tie it to one particular one, so you'll reference particular bits of geometry in a particular Rhino file. And my advice there is just make sure you keep track of what Grasshopper definition belongs to what Rhino file, and just kind of give them similar names and stuff like that, because if you lose one or the other, then that can give you a bad day. Next, we got the edit menu. Again, fairly standard, copy, paste, stuff like that. And then we have got the view menu and the display menu, the next two. Quite what the difference between view and display is, don't ask me. I'm sure there is some logic to it. But these give you options for how Grasshopper looks, basically. And I'm going to recommend some settings to you. Change the defaults. The first one that I'm going to recommend is this option here in the view menu, which is obscure components. So I'm going to have that turned on. And if you don't have that turned on, basically what it does is it hides a load of components in this ribbon here for you. Essentially, it's there to, when people first open up Grasshopper, not blind them with a huge mass of icons just staring them right in the face, and make it a bit more friendly to them. But in my view, it just makes things a little bit more difficult to find, so it's a good idea to turn that on so that you can see more of the library just from looking at it. The next option here, which I'm going to recommend you have turned on, so it's already turned on here, but it isn't by default, I don't think, is this draw icons menu option. So this is a bit controversial. I think last time Laura told you to do the opposite of this, and probably the guys next week will have a completely different view. But I like draw icons. I think the icons are very well designed. I think it is better to get used to using those icons, because then it makes it easier to find stuff in the library where you can still see the same icons. Several components have different icons but have the same name. So several different reasons why I recommend that. What I'm going to do when teaching actually is I've got a plugin installed here which will allow me to display both the icons and the names simultaneously. So I'm going to be using that so that you can still see what components are called even though I'm using the icons. So that's a little bit personal preference, but if you want what you're doing in front of you to look like what I'm going to do on the screen, I suggest you have draw icons turned on. Until next week, when probably Vincenzo will tell you to do the opposite or something. But for now, that's what I recommend. So below that menu bar, we have this set of tabs here. And this is the component library, essentially. So these are little nuggets of functionality, little processes that you can use to build up your parametric definitions. So they're essentially equivalent to commands in Rhino, but they're componentized so that we can use them in Grasshopper. And many commands that are in Rhino have equivalents in Grasshopper, but not all of them. Sometimes they work a slightly different way, and sometimes they're called something slightly different. So it's not quite one-to-one between Rhino and Grasshopper, but generally speaking, there's a lot of similarity between the way they do different things. And if you are good at using Rhino, if you've practiced a lot with Rhino and you know how you would model something in Rhino, then that helps to figure out how you're going to model something in Grasshopper as well. So this library is organized into different tabs relevant to different things. So the first tab is params. This has a lot of components to do with bringing information into Grasshopper and letting you kind of toggle certain things and control it. Maths has a lot of mathematical functionality. Sets has a lot of stuff dealing with data structures, which is something we'll be talking about a lot. Vector has a lot of stuff to do with points and vectors, as the name suggests. Curve tab has a lot of stuff to do with curves, surface with surfaces, so on and so forth. Intersect to do with intersecting stuff. Transform is to do with modifying stuff, so moving it, scaling it, rotating it, stuff like that. Display has a load of stuff to do with actually showing stuff on the screen and rendering it. And then these two tabs at the end here, which you may or may not have. Kangaroo, that's a plugin. So when you install plugins in Rhino, you'll probably see other tabs popping up here that have the components for that plugin in them. Within each of these tabs, you have different groups as well. And at the bottom of each one of those boxes is the title of that group. And if you left click on that title block, you'll get a drop down which shows all of the different components in that group with their names. So if you haven't yet learned all several hundred icons and you want to see what the names are, then you can use that to actually see what they are. And also, if you have obscure components turned off for some reason, or if you have squished your Grasshopper window up like that, you won't necessarily see everything in this top view, but when you click on the button, you will. So you will see everything that's in that group then. Okay, and then below that, we have the main canvas, which is where we actually create our parametric models. So to begin with, we will start with a very, very simple example. What we're going to do is just take 2 points, it's been a long day, sorry. 2 points, and we will draw a straight line in between them. So if we're doing this in Rhino itself, we would just type in line and then select 2 points, and it would create a line between those 2 points. What we're going to do first of all is just see how we would do that in Grasshopper. So the first thing I'll do is just use the point command in Rhino twice to create 2 points that I'm going to use as my inputs. So I've created 2 points in Rhino. The first thing I'm going to want to do is to bring those objects into Grasshopper in a form that we can then manipulate and use as inputs to our process. So in order to bring these points over, what we're going to do is use this component here, the point component, which you can find in the geometry group under the params tab. So it's the first component in the first group on the first tab. So that should be hopefully fairly easy to find. So if you find that and hover over it, you'll see a little tooltip appear which will tell you the name of the component, in this case point, and a little description of what it does. And in this case, contains a collection of three-dimensional points. So these parameter components here, they're very often just ways of basically kind of storing geometry. They don't actually do anything to geometry, but they store it inside Grasshopper and they let you represent it and later use that in other processes. So if you left click on that icon and then move down onto the canvas and left click again, then you should see that you have now created a little orange box. And this little orange box is a Grasshopper component. So the first thing to note is that it is orange, and that color is significant. So in Grasshopper, the colors that components turn indicate various different things. If a component is orange like this, then that is a warning that that component isn't actually doing anything, usually. And the reason for that is generally because you haven't given it the data to work with. And if you hover your mouse over the little orange speech bubble that pops up in the top left-hand corner, top right-hand corner, sorry, it will then give you a little message that indicates what that problem is, which may or may not be super helpful. In this case, it says floating parameter put failed to collect data, which is basically Grasshopper's way of saying that this is an empty component that doesn't currently contain any data because we haven't given it any yet. So what we need to do is to give this component some data to hold. And we can do that by moving our mouse over the component and then right-clicking. And this will bring up the context menu for that component. And then we can go down in this context menu to an option just over halfway down, which is set one point. So find that and left click on it, and then as if by magic, Grasshopper will disappear. And Grasshopper has disappeared because it's now asking you to do something in Rhino. If we look at the command bar, it's saying point object to reference. So it's basically saying, give me a point object that you want to store in this component. So if I left click on one of those points, a couple of different things will happen. First of all, this component will go grey. And that color grey in Grasshopper is a good color. That usually means the component is working as it should be. If we hover over that component now, we'll see in the tooltip that it now says one locally defined value, reference point. So by hovering over it, we can get a tooltip which tells us what data is in there. And what you'll also see in Rhino is that now we have a little red cross drawn over that point. So let me go into top view to make that a bit bigger. So that little red cross is something that Grasshopper is just drawing over the top here to indicate that that bit of point geometry is inside Grasshopper. So that's brought in one of our points. If we now do exactly the same thing to bring in the second one, so go back up to params, geometry, point, left click, drop that down on the canvas, and then right click, set one point, and then choose the other point there. So you'll see another little red cross appearing there, and you'll see this component is also grey. If we left click on one of those components, then that component will go green because it's selected. So green in Grasshopper indicates that the component is currently selected. And when we select these components, you should also see that that little red cross in Rhino has also turned green. So we can tell which component in Grasshopper references which bit of geometry inside Rhino just by selecting it and then seeing which bit goes green. So we now got our two inputs brought into Grasshopper. Now what we want to do is to take those inputs, take those 2 points, and draw a straight line between them. So to do that, we'll need to find a component which can draw a straight line between 2 points. So we'll have a look under curve, because that seems likely. And then we'll have a look under primitive, because that seems fairly primitive operation to want to do. And that first component in that group there is called line, and if you hover over that, it says create a line between 2 points. So this is the component that we're going to use to actually draw our line. If we left click on that and drop it down onto the canvas, we'll get another component there. And this component is a bit more visually complicated than these 2 point parameter components. And that's because this component here actually represents a process. So these two parameter components, they just store a bit of data, they don't do anything with it. This component here is a process. It takes in inputs, and these are the two little nodules that we can see on the left hand side, which are labeled A and B. And it's got a little nodule on the right hand side, which is the outputs of that process. And if you hover your mouse over those labels, it will tell you what those inputs actually are and what data that expects. So if I hover my mouse over A, it will pop up and it will tell me that is the start point. So it wants me to put some data in there which indicates the start point of the line. If I hover over B, that's the line endpoint. And then if I go over to the right hand side and hover over L, that's the line segment that this component is going to produce. So what we'll do is we will take our 2 points here and we will use those as inputs to this component. And we can do that just by hovering our mouse over the little nodule on the right hand side. And then if you hold down the left mouse button and drag away from that, you'll start to see this snaky dashed arrow that starts to follow your mouse around. And if you move that down to A, it will snap on. And then if you release the mouse, you will now have this little wire, this little connection going from that component to this one. And what that wire indicates is that the data coming out of that component is going to be used as an input for this component. So the data is going to travel along that wire, go into this process here, and do something. So if you also do that with the second point component, plug that into B, then that will give this component the information that it needs to actually perform the process that it's designed to do. In this case, it will draw a straight line between those 2 points. So you now should see in Rhino a straight line, and if you hover over the output parameter L, it will now say in there one locally defined value line, and then it will tell you the length of that line. And that essentially is everything you need to know in order to use Grasshopper. So this is basically how Grasshopper works. You've got different inputs, different processes which have inputs on the left hand side and outputs on the right hand side. You can plug these things together in order to connect data between outputs and inputs, and thereby define your process. So creating a Grasshopper definition is essentially no more complicated than just drawing out a process diagram for what it is you want to do. That's basically how you can think about this. Each of the little boxes is a different process. Each of the connections between them is just some information that flows between those different processes. And what you can do is start to daisy chain these components together in order to take these simple little atomic processes and build up much, much more complicated definitions over time. So to demonstrate that, what we'll do is we'll take this line that we've created and we will pipe it. So we'll put a surface around it so that it looks a bit more solid, a bit more 3D. So to do that, we'll go to Surface, Freeform, and then find this pipe component. And then if you left click on that and drop that down onto the canvas, this is another process. It has its own inputs and outputs, again on the left hand side and the right hand side respectively. And if we hover over those, we can see what they do. So that first input there, C, is the curve that we are going to create a pipe around. So it's the center line of our pipe. So we can take our line output from our line segment component and we can plug it in there. And that will then create this pipe surface for us. So you'll note that we didn't actually need to plug anything into R and E. And that's because those inputs already have default values kind of defined for them. If you hover over those, you can see what they are. So R is the radius of that pipe, and that defaults to 1. So this pipe will have a radius of 1 unit. If we look down at E, we're not going to deal too much with this input here because it's sort of superfluous, but what this basically lets you do is to define the end style of this pipe. So you can either have open ends or closed ends or put some sort of pill ends on it. And the default value there is none. So these have default values, but we can, if we want to, override them by plugging things into that. So let's say that we want to control the radius of this pipe. So we'll need to somehow create a number, get a number as an input, and then we can plug that number into R in order to specify that radius value. And there are several different ways you can define a number, but one of the most common, one of the most fun, is to go to params, input, and then that first component there, if you hover over that, that says number slider. So this input group here, what this contains is essentially a set of little input widgets that you can use to manually control different bits of data of various kinds. If you left click on the number slider, drop that down onto the canvas. Oh, incidentally, I forgot to mention this before, but the camera controls inside Grasshopper work the same way that they do inside Rhino. So if you hold down the left mouse button, you can pan around. You can scroll in and out using the mouse wheel, or you can hold down the control key and the right mouse button and then move the mouse up and down and scroll in that way. So hopefully if you're used to using Rhino already, that comes fairly naturally to you. But anyway, back to number sliders. So when we drop this number slider down, what this gives us is a little widget where we've got a little slider here that we can drag backwards and forwards in order to define a numeric value. And on the right hand side of this is another little output nodule. So we can connect that output nodule to our input nodule in order to override the value that was in there already. And then we can control that radius with that slider just by moving that slider backwards and forwards. So we can drag that backwards and forwards, but there are a couple of things about this which aren't ideal. First of all, we can't go above 1. So currently this slider is set up to have a maximum value of 1, so we can't exceed that just using that slider. Also, if we go to the other extreme, if we set it down to 0, then you might notice that this component now goes red. So as I said before, colours in Grasshopper are important. Orange represents a warning. It usually just means you haven't given it all of the information it requires. Red is an error, and what that usually means is that it's got the information that it needs, but there's something wrong with that information. There's something going wrong in the process of using that information which is causing a problem. And again, you can hover over that little speech bubble in the top right hand corner in order to see what the problem is. And in this case, what it's saying is invalid radius value. And that's because that radius value is 0. It's trying to create a surface around that curve with a radius of 0, but it can't because a radius of 0 surface doesn't exist. It's just, that's no different from the line we started with, essentially. So this is trying to create a surface, and if it can't create a surface, it will fail. So it's not always a big deal when these things happen, because a lot of the time it fails for reasons that kind of make sense. So in this case, if we set that to 0, then you would expect that surface not to exist. But we can modify this slider, A, to increase its range so that we can have higher radius values if we want to, and B, to limit the range so that we can't select 0 anymore. And if we want to edit that, then we can right-click on that slider, which will bring up the context menu for that slider. And we can then go down and select Edit. Or alternatively, to get to exactly the same thing, we can hover our mouse over the title bar part of that slider and then double-click. Either way, it will bring up this little form here, which allows you to edit the properties of that slider. So we won't run through all of these, but we'll go through some of them. So the first thing we can modify is the name of that slider. And Grasshopper sliders are quite intelligent in that when you plug them into an input, they will automatically inherit the name of that input. So when I plugged that slider into R, it automatically renamed itself Radius, which is quite neat. However, if we want to override that, then we can do that by specifying a name in here. So maybe I want to be a bit more specific. I want to say, okay, that's actually the pipe radius. The rest of this stuff we'll skip over for now. Down the bottom here, we can specify the numeric domain of that slider. So we can specify the start and the end values of that slider. So if we go to min and then double click on that, we can type in a new minimum value. So I'll make that 0.01, something like that, just so that we can't now pull that slider down all the way to 0 and get a surface which doesn't exist at the other end. And we can also set the maximum. So if I double click on that, I can then type in, say, 5. And then if I click the little green tick, that will make that so. So by using this form, I can specify the maximum and minimum range of that slider. So now if I hit OK, I've now got a slider here where I can't go all the way down to 0, so I won't see that horrible red color ever again. But I can also increase that radius all the way up to 5 now. So, what's nice about what we've done here, as opposed to simply going into Rhino and then using the line command and then the pipe command, which would do the same thing, is that this is now parametrically defined. So if we change any one of those inputs, so if I, for example, click on that point there and drag it around, changes to that input will then be propagated throughout this definition. So when I move that point there, that is triggering an update of the data in that component there. That new data there is now passing along that wire into that component there. That's then triggering an update of that component. That is then producing a new line, which is being passed along here. And then that is triggering a refresh of the pipe as well. And in this case, it's not super impressive because it's a fairly basic operation, but hopefully you can see the potential here that you could set up much more complicated, much longer chains of components, and have whole buildings and whole other designs modeled which you can then control via a few simple input parameters which are easy to tweak, and will then give you the geometry that you want. So that's one advantage of Grasshopper. We'll talk about the next advantage in a minute, but one thing I just want to mention, which you may have already noticed, is that in Rhino you can see this sort of red tube, or green tube if it's selected, but if you try and click on it, if you try and select that geometry itself, you won't be able to. Likewise, if you were to save this file and then come back to it later, but you didn't open the Grasshopper file, then you see that that geometry disappeared somewhere. Or if you were to try and render it, it wouldn't show up in the render. It would appear to all intents and purposes as if this geometry didn't really exist inside Rhino. And that's because, for all intents and purposes, this geometry doesn't really exist inside Rhino yet. So what you're actually seeing here is something that Grasshopper is drawing in the Rhino viewport as a preview, but Grasshopper is not actually creating that geometry itself inside Rhino. It's kind of a virtual bit of geometry, even more so than all of this geometry is virtual. So if we did want to actually have that inside Rhino so that we could save it or render it or modify it manually, what we need to do is to bake that geometry into Rhino. So we need to create a physical copy, or physical, again in inverted commas, copy of that geometry inside Rhino. So to bake something, let's say I want to bake this tube, I can go to the component, hover my mouse over the middle part of that component. So it's important the part of the component that you click on. If you click on the middle of the component, then you'll get the context menu for that component itself. If you right click on one of the inputs, then you'll get the context menu for that input. If you right click just on the canvas, then you'll get the general context menu for the whole Grasshopper canvas. So make sure you right click in the middle of that component, and you should see the third option down in this context menu is this option here, bake, with a little picture of a fried egg next to it. If you left click that, it will give you some options for how you want to add that geometry into Rhino, so you can choose what layer you want to put it on, what color you want it to be, stuff like that. We'll just leave it as the defaults for now and then hit OK. And now inside Rhino, you should now be able to left click and actually select that geometry. That geometry now exists inside Rhino. You can do anything you want with it. You can save it, you can render it, you can pull it around. You can, delete it if you want to. But that geometry, once you've baked it, is no longer linked to the Grasshopper model anymore. So if I make any modifications to that shape that I baked, let's just put it into shaded mode so we can see it. I can do what I want to that shape. It's not going to affect Grasshopper, and I can adjust these inputs, and that will affect the geometry inside Grasshopper, but it won't affect that geometry that we baked out. So once you baked it out, that's it, it's fixed, it's set. If you want to update that geometry, then you're going to have to basically delete it and then rebake. So for that reason, I highly recommend when you are baking stuff out of Grasshopper that you employ kind of good layer control. You put stuff that you're baking out on a particular layer so that you can come back and find it and just delete it all in one go and then rebake when you want to. Otherwise, that can be a bit of a problem. Oh, and I've just realised that even though I said earlier I was going to be using a plugin which displays the names, I haven't actually done it. So I'm just going to pull down this bifocals component and stick it somewhere. You don't need to worry about that. You don't need to do it. All that component is doing is just then running this plugin, so that now each of these components is going to be tagged by its name. So you can now see the icons and the names of these components at the same time. Hopefully that satisfies everyone. So as I said before, one of the advantages of Grasshopper is this ability to parametrically link things together, to have a set of basic inputs. When you change it, that will propagate changes throughout the whole model. That's one of the advantages. The other advantage, or at least one of the other advantages, is that we can apply this same process over and over again on multiple bits of inputs in order to produce multiple outputs. So once we've set up this definition, we can actually now use this to create not just one line and one pipe, but many, many, many different lines and pipes without having to, manually repeat the process. So to demonstrate that, what we'll do is we will create a few more points. So I will go back to the point command, and I'll create 2 more points on the left-hand side there, and 2 more points on the right-hand side there. And then what we'll do is we will use this same definition. We won't have to actually change the definition at all, only the inputs. We will use this same definition in order to create lines between all of those points. So in order to do this, we'll go back to our point input components and right click. And below, so before we used set 1 point, below that we've got set multiple points. So if you left click that, then again Grasshopper will disappear. And it will ask you to select points, and you can just basically keep selecting points until you've had enough. So this will override whatever is in there already, so you do need to first of all select that first point that we had last time. And as you're drawing this out, it will kind of draw these blue lines behind it so you can see what points you've selected and in what order. And the order can be important, as we'll come on to in a minute. So select those 3 points on the left-hand side, and then once you've done that, either right-click or hit return, and then that will end that selection. It will take those 3 points and it will put them into Grasshopper. And having done that, what we should now see is that we now have 3 lines here, and 3 pipes, consequently, from each one of those 3 input points that we specified to this other point over here. And if we look in Grasshopper itself, that's changed as well. So if we look at this wire now coming out from the point component to our line A input, what we can see here is that this has now changed into a double line. And what that double line indicates is that more than one bit of data is being passed along that stream. So from this point component, we've only got 1 point in there. We can only see a single curve, a single wire. Coming out of this one, if we hover over that, it now says 3 locally defined values. And the way that it's visually representing that we've got more than 1 bit of data there is to draw this as a double line. So this is an option that you can turn off, by the way, but I suggest that you have it on. So up the top here, you've got this option here, which is draw fancy wires. I highly recommend you always keep that on because it's very, very useful. So when we have draw fancy wires turned on, which I think it is by default, we should see some indication on these wires of the amount of data that's passing through them and the way that that data is structured. So we've now got 3 points coming out of here, going into A. We've got 1 point coming out of here and going into B. So now let's set multiple points and select those 3 points. So now, well, before you do that, just have a think about what you actually expect the output from this to be. Because there's several different ways that Grasshopper could interpret this. And if we left click on each one of those and hit return, we'll see the way that Grasshopper does actually deal with that. So what's happening now is we've got 3 points coming out from that component and 3 points coming out from that component. And what this component is doing is something which is very important to understand in Grasshopper, that's called data matching. What data matching is when you have multiple bits of data going into a component input that normally only takes one bit of data, such as these 2 point inputs on our line component. What Grasshopper will do is it will look at the first item in the first list going into the first input, and it will say, okay, I'll take that. That's going to be the first thing I look at. It will then look at the next one, and it will take the first item in that list, and it will essentially match those 2 things up, and it will then run once for that particular set of inputs. What it will next do is it will then look at the second item in the first list and the second item in the second list, and it will then run again for those pairs. So it will pair up, or however many inputs you've got, it will match up different sets of input data based on their position in the input list. So this is the first rule of data matching. So the first rule of data matching is components that work with single items at once will match up items in input lists in order. First with first, second with second, third with third, fourth with fourth, and so on and so forth, until it gets to the end of each of those lists. So this is the first rule of data matching. And again, this is very important to understand. So I said before that all you needed to know about Grasshopper was that you can, connect inputs together. The second thing that you need to know about Grasshopper is this rule here. So this rule applies where you have 2 lists of data, or multiple lists of data. It can be more than 2. It doesn't have to just be points either. It could be any type of data. Of multiple points of data coming into a component in lists, where those lists are all the same length. What happens, however, if these 2 lists are not the same length? Again, there's several different ways that Grasshopper could deal with this, so place your bets amongst yourselves what that's going to be. But we can have a look at this by going back to the second point component, going to set multiple points, and this time around what I'll do is I'll just pick those first 2 points in there. So now what's happening is we've got 3 points, 3 bits of data coming out of that component, but only 2 bits of data coming out of that one. And what this component is doing is it is taking the first bit of data from that first list, it's taking the first bit of data from that second list, it's making that a pair, it's running once that process for those 2 inputs. It's then doing the same thing for the second one, so it's taking the second from the first list and the second from the second list, and it's matching those up and it's using those. And then it's getting to the third item in that first list, and it's taking that and then it's looking at the second list and it's going, oh, there is no equivalent index here. I can't match that up with an equivalent, so what I'll do is I'll just take that last item in that list again. So what's happening is that this point here is being matched up to that point there again. It's reusing that last point. And it will do this so that, for example, here we have 3 curves coming in, but we only have 1 slider, so it's using that 1 slider for all 3 curves. So that is the second rule of data matching. So the second rule is, if there is no equivalently indexed item in all lists, the last item in the list will be used instead. So these 2 rules are very, very important. They come up again and again and again. we're going to be talking a lot about them in this course. A key to kind of understanding how Grasshopper works and getting Grasshopper to act the way you want is understanding this behavior, and then learning how you can essentially, cheat it and get around it where you need to. So obviously the order that these things are selected in is important. So if I go set multiple points and this time I select them in reverse order, then these things are going to start crossing over. If I set those free again that way. So one implication of these data matching rules is that the order things are entered in, the order that they're produced in, the order that they're outputted from components in is important because that's the order they were matched up in. So you can save this if you want to. So we'll go File, Save Document. Is Andrew around? Or did he go? I'll just save it on his desktop. It'll be fine. So that's the end of the first example. But what we're actually going to do in the second example is just take this and work on it a bit more, expand it a bit more. What we're going to do is actually look at the way this works with longer lists of data, but we're not going to manually input all of that. What we're instead going to do is create these points here parametrically from a pair of curves. So rather than just creating a single line between 2 points or several sets of lines between 2 points, what we're going to generate here is a kind of ladder structure. So we'll take in 2 rails and then we'll generate rungs between them. So we can delete all this stuff if we want to. You can save it if you want, obviously. And when we delete that data inside Rhino, you'll see that these now go orange again because that data has been lost. These components now no longer actually represent anything. So what we're going to do is we're going to insert a bit ahead of this part of the definition. So if you want to, you can left click and select that and then drag it a bit of the way over that way. This border that you see here, you can actually work over that perfectly fine. That border isn't really a hard limit. It's just kind of it's just a way of kind of giving you a reference point to work with. So you can just ignore that if you want. Also, if you have a larger definition and you want to create some space in it, and you want to essentially shift all of the components in it over a bit so that you've got some room to work with, then what you can do is hold down the Alt key and the left mouse button, and then if you drag out there, it basically gives you the option then to shunt everything in that definition over a little bit, which is quite useful. So very often inside Grasshopper you'll build something and then you'll think, actually I want to change the way that that is working. I want to work backwards from that in order to get to the inputs that I want to give it. So you have to be used in Grasshopper to sometimes working a little bit non-linearly and kind of starting at the end and going backwards, or starting in the middle and working outwards, or starting from both ends and then kind of figuring out how you're going to meet in the middle. So what we'll do here is I will just shunt that over a bit, and what I'll do is I'll change the inputs that we're using, and I'm going to change the inputs to 2 curves. So I will go back to Rhino and I'll just use the curve command, or you can click that button there to do the same thing, and then I will just draw out 2 sort of parallel-y but not really wibbly wobbly curves. So what I'll do with these now is I'll take these curves, I will create an evenly spaced set of points along them, and then we can use those points as our points to plug in here and create our lines and create our pipes. So if we want to bring in these 2 curves, then we can do it in a very, very similar way to the way that we brought in those 2 points, or 6 points, or however many points in the last example. We can go to the params tab, we can go to the geometry group, and then we can find this curve parameter component. And then we can left click on that and drop that down on the canvas. So using this ribbon, this library of components up here, is one way that we can create components, but it's not actually the only way. We do have another option. So if you don't know where the particular component that you want is stored in here, or you have no idea if a component to do what you want even exists, what you can also do is put your mouse somewhere over the canvas and then double left click, and what will come up is essentially a little search box, and you can type stuff in that in order to search for components by name or by function. So if I type in curve, what it will come up and suggest is a whole load of different components, all to do with curves. So that curve parameter component that we want is that first one there. And if you left click on that, or if you hit return, it will add that to the canvas in the place that you double clicked. So that's the second way that you can create components. And that may be the way that you prefer. Generally speaking, when I'm doing this, I'm going to be using stuff from the library up here, just so you can kind of see where it is, and so you can get used to looking around that for similar components. But probably, again, other people will, turn all the icons off and they'll be double clicking for everything, and there's nothing, strictly speaking, wrong with that. So feel free to do it whichever way makes you more comfortable. If you miss a bit and you can't see where I got it from this ribbon, then obviously you can double click and then type in the name of the component and find it that way instead. So we brought down 2 curve parameter components, and if we right click on those, then go down to set one curve. So in the point parameter component we had set one point, here we had set one curve. You may see a pattern emerging here. A lot of these parameter components basically do exactly the same thing, but for different types of geometry. Or different types of data, not even necessarily. So if you right click on that, go to set one curve, and then you can select one of those curves, and we'll do the same thing for the second one in order to bring both of those curves in. The next thing that I said I wanted to do is to take those curves and then divide those curves up and get a set of evenly spaced points along those curves. And this is a very common thing to want to do, especially for structural engineers, because we often want to space things out equally, like columns and beams and so on. So this is quite a useful component. If you go to the curve tab, look in the division group, then there is a component there called divide curve. And this works like the divide command inside Rhino, if you've ever used that. What it will do is it will divide up the curve into a certain number of segments, and then it will give you the points sort of in between those segments. So pull down a divide curve component, or if you don't want to do that, you can double click and then type in divide curve and get one that way. But in any case, we want 2 of these, 1 for each curve. So if we look at the inputs here, C is the curve to divide. So we can plug our input curves into that. And you'll see that it now has created a set of evenly spaced points along that curve. And these will actually be evenly spaced, incidentally. So what I was saying before about curve parameters not necessarily being evenly spaced is true, but in this case, this is actually dividing it up based on length rather than parameter space. So you can divide up curves by getting their domain, dividing up that domain, and then pulling out points from that. But doing it that way will mean that your points are not necessarily going to be evenly spaced. I just throw that out there as a warning because that's the kind of thing that if you don't know about it can seriously bite you on the bum. So the C input is the curve to divide. N is the number of segments that we're going to divide that curve into. And just note here that this is the number of segments that you're going to divide that curve into. It's not the number of points that you will get. If you've got an open curve, you will get one more point than this number. And that's because it will say, okay, I'll divide this into 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 different segments. And then it will put a point on the sort of ends of that, but you'll also get an extra one at the end here. So you, in this case, it's defaulted to 10 segments, but you'll get 11 points. That doesn't apply if it's a closed curve because the start and end point will be the same, so then you'll get the same number of points as you have components. Again, it doesn't really matter for this purposes, but I just thought I'd point that out. This K input here, we won't worry about because it doesn't apply here. Basically, that's a little toggle. If you set that to true, then it will put a division point at any kink points that you have in that curve. In this case, I've got smooth curves, so it's not going to matter either way. And then on the right-hand side, our outputs are P, which is our set of division points, and that's what we want in this case. So we can take that P output and we can plug that into the input of our point parameter component that we had before in order to replace any data that's in that with the outputs of that component. So just to run through the other outputs here, the big T will give you your tangents, and what that essentially means is it will give you the vector which describes the direction that the curve is heading in at each one of these points. It's useful, not in this case, but it is generally quite useful. The little t is that parameter value that I talked about before. So that is the parameter value at each one of those points. And that's useful here because if you wanted to find out more information about the curve at that point, say you wanted to find out what the radius of the curve at that point is or something like that, then there are components which let you plug in that curve, plug in that t value, and can give you a bit more information about that curve here. Again, we're not going to actually use it here, but that's what that output is. So we got this working for one set of points. We'll now do the same thing for the second set. So plug our curve into the C input and plug our P output into our point component. And now we've got a set of pipes that run between these two curves. So after this point, it's exactly the same as what we had before. We've just inserted a bit before that, which will generate those points by evenly spacing them along two curves. This N input here has defaulted to 10, but again, we can override that with our own value if we want to. So we'll use a number slider to do that. So drop one down. And again, we come into the problem here that by default, these number sliders can only go between 0 and 1, so we want to modify that. So again, right click, go to edit. And what we can do in here, we can specify the maximum, so I'll set that to be, say, 20 instead of 1. And what we can also set in here is the kind of accuracy of that slider. So how many decimal places that slider gives you. So if you want to be super accurate, you can set this very high and you can get, sub-millimeter precision. In this case, we can only ever divide this curve by whole numbers anyway. That's how the divide curve component works. If you give it a kind of floating point number, a decimal number, then it will simply just round to the nearest whole number anyway. So we might as well, just to make it easier to control this, set this slider up so that we can only give it whole numbers. And there's actually two ways we could do this. We could get this digits slider here, and we could pull that all the way down to 0. So that will mean there's no decimal places allowed in this slider. Or the other way of doing that is to click on this N icon here. And what that will do is set this slider to integer mode, so it can only take integers, i.e. whole numbers. There's two different ways of doing it. What you can also do with this is using these E or O options here, set it to only take even or odd numbers, if that's something you want to do. So we'll hit OK, and now we can control the number of points along one curve. So if we plug that slider into both of them, then we can now control the number of bars that we have between them. But what we can also do is set these so that they have independent sliders. So we'll create another slider. Probably the easiest way of doing this actually is just to select that slider and then Control C and Control V to create a copy. But while I'm here, I will also show you another way of creating sliders, and that is through the double click method. So if you double click on the canvas and get that search keyboard up, then you can get a number slider just by typing in number slider, and then find it. However, what you can also do here, what this search box has built into it, is certain little shortcuts that allow you to do certain things through shorthand. So what we can do here is, rather than typing in number slider, we can just type in a number. So if I type in the number 10, or actually let's type in the number 13 instead, actually, then what will happen is it will pop up and it will suggest number slider for that just by typing in a number. And then if you hit return, what it will do is it will create a slider set up so that it is got the initial value that you put in. So in this case 13, that's what its initial value is. It's got the accuracy to the number of decimal places you specified. So if you put in no decimal places, as in this case, it will set the slider up to only snap to whole numbers. If I was to type in 13.00 instead, then it would give me 2 decimal places and so on. And what it will also do is it will set up what it thinks is a reasonable range around that number. So it will basically be the order of magnitude that number is in. So what it's done here is set it up to 0 all the way up to 100. So if I gave it a number between 1 and 10, say 5, then it would set it up between 1 and 10. If I gave it a number which was 5,080,000, then it would give me 0 to 10 million. So you can use that as a shortcut just to very quickly set up number sliders without having to keep going up here and then going into those options and setting it all up. What we can also do, if I type in here a number followed by 2 dots and then another number, so in this case I typed in 0.20, that will set up a number slider between those two numbers. So I can specify the start value of the domain, ... and then the end value of the domain, and it will set up a slider there. Again, accurate to the number of decimal places that you specified. So that's a handy little shortcut. So if I plug that then into N on that second one, then we have these 2 sliders here now, and we can play around with these independently, and you can see the effects that has. So you can see here that those 2 data matching rules are in full effect, whatever values I put in here. So if I put more values into this slider than that one, then when it gets to the end of this set of points, it will just keep reusing that last point. And vice versa, if I do it the other way around, then it will use the last point of this set. So this is kind of the hard-coded behavior of Grasshopper. And there's not a lot we can do to change that. But what we can do, in order to get it to work differently, is to manipulate the data that we're feeding into it. So let's imagine that instead of it using that last item over and over and over and over again, we instead want it to get to that last item and then just stop. Back in the good old days, there was actually an option on different components that would tell it to do that, but nowadays they've taken that out. So we can't do that anymore, but what we can do is get that same behavior using this component here. So this is on the Sets tab in the List group. It's called Shortest List. If I drop that down somewhere around there, what this component will do is it will take in multiple lists of data and it will essentially make them all the same length. So if I plug my P output from there into A and my P output from there into B, and then I plug the outputs there into the relevant point components to replace what we had there before. What this component will do is it will take in these two input lists. It will say, okay, I've got 14 values coming into A, I've got 20 values coming into B. I'll take that longer list and I will essentially chop the end off it so that they are both the same length. So I will make it so that A has 14 items in it and B has 14 items in it as well. So we can use this in order to modify that basic Grasshopper behavior where it will reuse that last item. We can't change the way Grasshopper works, but we can basically just edit that data before we give it to it so that we don't have that effect actually taking hold anymore. Alternatively, maybe what we want to do instead is to actually, rather than pairing these things off, maybe we instead want to connect every single point on one side to every single point on the other side. Maybe we want to create this kind of cat's cradle effect where we create a network between these two sets of points. And we can do that as well. So if I get rid of that shortest list component and I instead replace it with this component here, which is called cross-reference. So this is again from sets list. And then we drop that down on the canvas. This works in a similar sort of way, except rather than manipulating these lists so that they're all the same length, what this will do is manipulate these lists so that it is pairing up every single point in that first list with every single point in that second list. So it's a little bit difficult to tell now because it's all a big mess. Let me reduce that radius slightly. Uh-oh. So hopefully you can see now what this has done is this has got Grasshopper to take all of these points along here, and then for each one of those points it's connecting that to all of the points over there on the other one. But again, this is still following the same data matching rules. So what this is doing, it's taking list A in, it's saying, okay, I've got 12 values there. And it's taking list B in, it's saying, okay, I've got 9 values there. And then what it's spitting out the other side, so it's taking list A, and then it is taking that list, and it is just repeating that list over and over again until it's got the same, until it's got one set of each of those for each thing in B. Whereas in B what it's doing, if you look at that, is it's taking each item in that list and it's then just repeating that a certain number of times until it has made all of those possible combinations. So this you can use in order to create these kind of networks, these kind of cat's cradle things. So key things to remember from this are, first of all, those data matching rules, and also that they can be kind of circumvented where necessary. So we'll stop doing this now. We'll get rid of that component and we'll just have the default behavior. And what we'll actually do is I'll get rid of one of these sliders and make it so that we do always have these same number of points on each side. So we've gone back to having, a nice regularly spaced ladder. And what we'll just do finally in this session, just to make this slightly more interesting, is we will turn this into an actual kind of structure. So rather than having this as a simple set of 2D lines, what we could also do is turn this into a kind of a tunnel. So rather than having straight lines joining these 2 points, what we'll have is a set of arcs which join these 2 points and kind of poke up in the air like that. So to do that, what we need to do is replace this line component here with, instead, from the curve tab, one of these arc components. So there's several different arc components, but the one that we'll use is this component here called arc SED. So find that on the ribbon or type it in, and then drop that down onto the canvas, and you can delete that line component, and instead we'll replace it with this arc component. So the inputs for this arc component are fairly similar. First of all, we've got S, which is the start point of the arc, so I can plug one of my points into that. We've got E, which is the end point of the arc, so we'll plug our second point into that. And then we've also got this third additional input, and if you hover over that, what that's asking for there is the direction, the tangent at the start of that arc. So this is, what it's asking for here is a vector which describes the direction that arc is going to be start pointing in. So we need to give this a vector. So we'll go back to the vector tab. So hopefully you guys are engineers, you know a little bit about vectors already. Vectors are very useful, obviously, very useful generally, they're very useful inside Grasshopper as well. So there's different ways that we can set up vectors. Vectors and points inside Rhino and Grasshopper are simply basically little data structures that hold X, Y, Z coordinates. You can use them interchangeably easily. So components will ask for points or they will ask for vectors, but you can usually plug a point in when it asks for a vector or a vector in when it asks for a point. You can add them together, you can treat them the same. Essentially, points and vectors are both vectors, it's just points are kind of a special case which implies certain other things. In any case, what we want to put in here is a vector which essentially points directly upwards, so that we have our arcs passing between these 2 points, but also being erect, being pointing upwards in the Z direction. So in order to do that, we'll use this component here called unit Z. And if we wanted these to go in different directions, we could use other components in here to create that, but what we'll do here is we'll just take that unit Z vector and we'll drop that down. And what this creates, if you hover over the output here, is just a unit vector pointing up along the global z-axis. So what that translates to is a vector which has the coordinates x equals 0, y equals 0, z equals 1. You take that vector, you can plug it into D, and you should then see that we've started to get this set of arches appearing between those two curves. So let's use these arcs now in order to create a kind of freeform roof, which is going to follow that geometry. And we can do that using a component called loft. So you may have come across the loft command in Rhino, which allows you to basically take a set of section curves and then create a surface between them. Works exactly the same way inside Grasshopper. So we can go to the Surface tab and then find this component here, which is called Loft. So if you hover over that, it says create a lofted surface through a set of section curves. And if we drop that down onto the canvas, this first input here, C, is the curves that you want to build a surface through. So we will use the A output from our arc SED component, which is those actual arcs that it's creating. So we can plug A there into C, and that will then create this lofted surface, creating a kind of igloo tunnel thing, which represents our geometry. So what's interesting to note about this loft component, and we'll kind of return to this in later sessions, is that if you hover over the input there and look at what type of data it's asking for, it's saying there curves C as list. So different types of components take in data in different ways. Most components, so most of these ones we've been using here, take in a single bit of data and then they'll match up. If you put multiple bits of data in there, it will match up that with the other inputs and produce data accordingly. In the case of this loft component, this C input here wants a list of objects to begin with. If you only give it one object, then it's not going to work at all. It actually needs a list of objects, and it will work on that whole list of objects in one go. So we'll come back to this and the implications of it in later sessions, but in this case, what that does is it slightly distorts that data matching logic. So that data matching logic still applies, but in a slightly different way, which we'll talk about in later sessions. So that we use that to generate the kind of roof surface of our structure. And if you want to change how that looks, then if you right-click on that O input, you can specify the loft options in here in the same way that you could inside Rhino. So let's say we want to make this loft so that it's got straight sections in between those arc ribs. We could set the loft option there to straight and then click commit changes, and then that would kind of facet that surface in between. You can do that if you want or not, it's entirely up to you. What we can also do is reintroduce our pipe component here. So we can use our arc output and reuse that, plug that into this pipe component here. And then we can use that to create structural ribs, which are going to support this freeform geometry. So we're starting to think a bit more like engineers here. And if I was looking at this and I was thinking as an engineer, which occasionally I do because I am one, what I might think about this is that these arcs are all different spans. And therefore, some of these arcs, or some of these arches are going to be working harder than others because they're going to be, spanning further, supporting more weight. What I might want to do is therefore not have the same cross-section for each one of these ribs. Some of these I might want to have a deeper section. And maybe what I want to do is to have Grasshopper automatically select the size of that section for me based on the geometry. So now I'm starting to input my design thinking, my kind of structural knowledge, and I'm starting to embed that into the definition. So this is where that stuff I talked about earlier, about kind of taking the logic behind that design and working it into the model itself, you can actually start to do that, and it becomes a lot more powerful then. So what we'll do is, rather than just having one radius value, we'll have a different radius value for each one of these arcs. And we could do that by plugging in different sliders. So actually, if I just copy and paste that slider a few times, I can actually plug multiple sliders into this input. So I can create a list just by using different sliders. I can't do this by default though. If I try and pull out from that and connect it into that R input, then when I try and make a new connection there, it will just overwrite the old one and I'll lose the old one. But you can put multiple bits of data into the same input if you hold down the shift key while you're making that connection. So if you hold down the shift key and then you drag out and make that connection, then you can plug multiple outputs into the same input. And what it will essentially do is assemble that then into a list of data there, to which data matching rules will apply. So here I've got 3 sliders, and now I can control these reasonably independently. So I can control at least the first 2 arcs independently. And then, because those data matching rules are applied, I've only got 3 values here, but I've got lots of different values coming in there, so it's just reusing this last value for all of those ones. So I could have an independent slider for each one, but that's not going to be a great way of doing it, because then if I change the number of arches that I've got, or if I modify this geometry, I'm going to want to come back and modify that manually. I'm maybe going to need to add more sliders or take them away or something like that. So we won't do it this way. So if we want to remove connections incidentally, then we can do that as well, either by right-clicking on an input and then going to disconnect, and then you can select the various inputs connected to that individually and left-click to remove them. What you can also do to remove connections is to hold down the control key and then essentially trace over the connection that you made. So if you hold down control and then you drag out from a nodule to another one where a connection already exists, then holding down that control key will essentially delete that same thing. Or we can just get rid of it, or we can just replace what we got in there. So we don't want to use sliders for this. Or at least not individual sliders. What we're going to do instead is embed some structural logic into this. So what we're going to do is say, we will make the radius of this tube, the size of our section, dependent on the span of these arcs. So what we can do, and what we will do, is we will find the distance between these 2 points, and then we will use that as a driver to select the size of our section. So if we want to calculate the distance between 2 points, let's think about where that's likely to be. Points are vectors essentially in Grasshopper. So we'll have a look on the vector tab, have a look in the point group, and there's a component there called distance, which is what we're going to use. Or, of course, you could just double-click, type in distance, and find it that way. But what this component does is it just takes in 2 points, A and B, and it will give you the distance between them. So if I plug that first list of points into A and that second list of points into B, then I will get a set of distance values out the other end, which is the distance from each of these pairs of points. And again, it's applying the same data matching logic here as it's applying there. And what's important here is that we will end up having a set of distance values coming out the other end which match that set of arcs. So it will be in the data which relates to each arc will be in a list which matches that structure. So we'll have the first distance will be related to the first arc, the second distance will be related to the second arc, and so on and so forth. And that allows us to, keep using Grasshopper's data matching logic in order to relate those two qualities. So we don't want to just plug this in here because otherwise we'd end up with supermassive radii. So instead what we'll do is we will multiply that distance by this value here, which is going to be now a factor that we're going to apply to that. So we're not going to use this slider anymore to directly set the radius. What we'll do instead is we'll multiply this value by the distance in order to generate our final radius. And to do a multiplication, we can go to the Maths tab, we can go to the Operators group, and then we can select this multiplication component. And what this lets us do is simply multiply two numbers together. So we'll multiply our distance, going to A, by our slider, and then we will plug the output of that into R. And you might then need to reduce that slider a bit. In fact, let's go in and change the maximum down to 0.1, say. And now what we're doing, because each one of these distance values relates to a different arc, when we plug them back in here, it will match up the distance value that applies to that arc with the arc itself, and then the pipe that it creates will have a radius depending on that parameter. So we're relating two different bits of data here, one which is the result of analysis, even if it's a very simple analysis, just comparing the distance, and one which is matching that up to the geometry to which it relates. And then based on that, we can build up our structural logic so that we are automatically sizing these ribs based on that distance. And of course, if we were doing this properly, then we'd probably want to be a bit more analytical about that. We'd probably want to come up with a better rule. But we can now play around with this and see in real time. So if I turn on control points, I can play around with these curves, and I can start to see what effect that has on the structure. So thanks very much for listening. That's the end of today's session. I think I finished bang on time there. If you have any questions, then we'll be around for a few more minutes afterwards. And Paul Cowell is here. I believe he wants to talk a bit about getting your money off you. Is that right, Paul?
Yeah, pretty much.